You want to get garlic on the side there? So are we good? Do I need to log in?
I think we're good.
Should I see if I can see it on that app?
Well, it says live.
Let me text Erica. Good morning. We're going to just wait a few minutes. I think that they were running a little over in there. Erica says there's a bit of an echo. So let's.
What's she say?
Erica says there's a bit of an echo.
And probably help. What would it help
There's an echo on the live stream.
on the lives?
We're live streaming this session. Still an echo, Erica?
If you're on the live stream there,
I'm not.
okay.
No, we're just texting each other.
Okay. Yeah, I mean, you should be good.
To this one?
Okay, she said it's in the background, just very faint. So do you think we're good to go ahead?
I think you're good to go ahead, because when I shut these doors, it's gonna shut out that noise, and I don't think anyone in here is logged on to the Zoom meeting.
No, I don't think they
So
are.
yeah, I think you're gonna be in good shape. If you want, I can give you my number, text me.
Yeah, thank you. Do you need to add that one in my purse? I just want.
That's good. All right, I got one. This kind of
Yes,
person.
no worries.
Thank you. Yeah, that's what Eric said. Well, I think when the doors are closed, it will help. All right. Great, thank you. So should we go ahead and get started?
Yeah.
All right, let's go ahead. So my name is Christy Duke. I am an epidemiologist with USET. Just wanted to let you guys know that these sessions are being, I'm going to take this off while I'm talking so you can hear me better. All the sessions are being recorded and will be available for viewing for up to 3 months following the conference using the links in your agenda and calendar invitations. Materials available for this session are provided by the presenters. So we can get you printouts if you would like to have those for the session. So with that said, I am first going to introduce, this is our Improving Patient Care Through Data Track. Our first session will be focused on biostatistics and epidemiology, and I'd like to introduce Brian Hendricks and Anna Garrett. They are our presenters. I'll read Brian's bio now, and then Anna will read yours when we transition. Brian Hudson Hendricks is an employee of USET for almost 10 years now as a quality improvement data analyst. In this position, Brian is responsible for the GIPR Improvement Pilot Project, Immunization Program, HIV and Harm Reduction Program, and the Project EGNO program. So Brian has his hands in a little bit of everything. In these projects and programs, he conducts trainings and webinars on the electronic health record, resource and patient management system, eye care, national immunization reporting system, and multiple state immunization registries. The Project ECHO program was created at USET in 2018 in partnership with the University of New Mexico's Project ECHO model and currently has 3 successful clinics: hepatitis C, COVID-19, and behavioral health. There are 2, HIV PrEP and substance use disorder, currently in the beginning planning phases. The most recent Project ECHO clinic to launch was the Behavioral Health ECHO, titled Reclaiming Native Psychological Brilliance. As you can see from our keynote speaker, she is tied into that Project ECHO section. Its inaugural launch had over 300 registrants. Brian is an alumnus of Middle Tennessee State University, where he received both his Bachelor's of Science in Statistics and Master's of Science in Biostats. In addition to these degrees, Brian is also certified in base SAS, Technology of Participation, and is currently working to be certified in public health, getting his CPH. So with that said, Brian, I will turn it over to you, and you can tell them all about Biostats. Thank you.
Thank you. Sorry for the long bio. I need to fix that. I'm going to be talking about biostats today. I'll go. So biostats. Don't run away, please. Don't hide in the corner. It's okay. And please, whatever you do, don't bite me. I love ponies. Okay, so what is biostats? It's the methods of dealing with statistics in the fields of medicine and public health. Deals with the development of applications for collection, presentation, analysis, and interpretation, and making decisions on those results, on the data. I have to go through these quickly because I have a lot of slides. So statistics, there's 3 main parts of, okay. There's 3 main parts of statistics. There's descriptive, experimental, and inferential statistics. And I'll go into all of those except for experimental because we don't have time. That's biostats 1 or 2. Descriptive statistics is summarizing and describing the data. Uses numbers and graphs to interpret the data or characterize the sample data. Data is a set of values recorded on 1 or more observational units. They're raw materials of statistics. Sources of data, you have experiments, surveys, and records, health records, and different types of records. Sources of data, records, surveys, and experiments. Information regarding the mode of transportation used by patients to visit the clinic. Or you wish to know which strategies is best for maximizing your outputs. Or average patient BMI. So those are all examples of sources of data. Types of data. You have quantitative and qualitative. Your quantitative is going to be your numbers. Your qualitative is going to be your categorical. And I'll go into these 2 types too. So your qualitative is going to be more of your surveys, and quantitative is more numbers and records. So quantitative can be used in, or can be measured in the usual sense. For example, the heights of adult males, the weights of preschool children, the ages of patients seen in a dental clinic. Qualitative data is many characteristics are not capable of being measured. So some of them can be ordered and ranked. So for example, the classification of people into socioeconomic groups, social classes based on income, education, etc. I'm going to focus mostly on quantitative data. Discrete variables and continuous variables are 2 types of quantitative data. Discrete is characterized by gaps or interruptions in the values that it can assume, meaning that there's precise numbers that the data is. And continuous is can assume any value within a specified relevant interval. For example, height and weight. So for however many people, like Christy and I may be the same height, like 5'8" and or 5'7", 5'7" and 5'8". There's got to be someone that's going to be in between us in the world. So that's continuous. There's going to be someone continually in between each person. Does that make sense? Population. Population is the largest collection of values of a random variable for which we have interest at a particular time. For example, patients with diabetes at a specific clinic, or patients who use drugs seen as strange services. However, it is not practical to always survey the entire population. So you have to make a sample of that population. So that sample has to be random. It doesn't have to be random. If it's not random, then it can lead to bias, and that's not good. You want something that's representative of the entire population. So you want it to be random. Types of statistical methods: descriptive and inferential. We mentioned earlier. Just went over descriptive statistics. Inferential is where you infer on the population. And I'll go into that in just a little bit. First, we'll go into descriptive statistics. Strategies for understanding the meanings of data. I'll get on top. Okay. Measures of central tendency. So this is your mean, median, and mode. I'm not going to talk about median and mode because we don't really use those in health statistics. We use mostly mean. I can see some instances we use others, but mean is the arithmetic average of a variable X. Its preferred measure is the interval or ratio variables with relatively symmetric observations. It does have good sampling stability, implying that it is better suited for making inferences on the population that we mentioned earlier, inferential statistics. It is affected by extreme values, the outliers. So anything that's outside the mean is gonna, I don't know, measures of dispersion. Measures of variability depict how similar observations of a variable tend to be. The measures of dispersion describes the degree of variations or dispersion of the data around the central values. So there's three of these that we can go over, that we're only going to go over one. We're going to go over standard deviation, but there's also range and confidence of variation, coefficient of variation. I can't see. Standard deviation, it represents the average spread of the data around the mean. So there's the formula. Don't want to drop that. That's very important. Summarizes the deviations of a large distribution from the mean in one figure used as a unit of variation. It indicates whether the variation of difference of an individual from the mean is by chance, natural, or real, or due to some special reason. So that means that this is a normal distribution. People online can't see me. This is a normal distribution. Your mu is mean, that's mu. And your, what's that called? I can't remember. Anyway, whatever that one is. That one's your standard deviation represented. So your mean is in the middle. And this is one standard deviation. then 2 standard deviations, then 3 standard deviations, then 4 standard deviations. On each side will cover the entire spread of your sample, or entire population. And I'm going to come back to this. Oh. So the 65, 95, 68, 95, 97 rule. You ready? It's going to be fun. Okay. The confidence interval, the interval within which a parameter value is expected to lie with a certain confidence level as could be revealed by repeated samples. So I'm 95% confident that the rate of diabetes for the X tribal nation falls between Y and Z. 1 minus X% is standard error, just FYI. Okay, going back to this. Here's your Y, X and Y is what that means. So I'm 95% confident. So here's 68, here's 95, and here's 97. So in this area right here, you would be 68% certain that your data falls between these 2 standard deviations. You would be 95% in these 2 and 97% in those 2. That clears mud. Okay. So with that, we go into inferential statistics. So inferential statistics provides a way to draw conclusions about broad groups of populations based on a set of sample data. Does anybody deal with diabetes populations and audits, diabetes audits? So y'all know y'all have to take a sample and then we can infer on the entire population of diabetic patients in your tribal nation. So we're going to talk about Hep C in tribal nation. 23%, and this is just random, I just made up numbers. 23% with the standard deviation of 2% of the sample that we took of patients randomly selected had been diagnosed in their lifetime with Hep C. So remember the 68, 95, 99 rule? You can infer that with 95% confidence that 19 to 27% of the actual tribal population has had an Hep C diagnosis in their lifetime because we took 2 standard deviations. So 2 away from that is 19 on this side, and then 2 on this side is 27. So let's go back to this one. There's your 23. There's your 21, 19. 25, 27. So that's your confidence interval. So you can infer on that. So recap. We went over data and data sources, types of data, types of qualitative data, population and samples, descriptive and inferential statistics, measures of central tendency, mean, median, and mode, which we can go over median and mode. Measures of dispersion, standard deviation, and confidence intervals. So you got a whole semester's worth. Thank you. So do y'all have any questions? I'm gonna go ahead and take questions since I have time. Do y'all have any questions about statistics that you want to ask me? Anything at all? Yeah.
What's your favorite statistical test to run?
Oh I like the one where you, I can't remember. No, the t-test. I love t-test, but I'll have to get back to you on that one.
Too many to choose from.
Because there was one that we did for cancer research, to see how long it would, this is really morbid, how long it would take someone to die with terminal cancer. I can't remember what it's called.
Logistic regression, using regression.
I do love linear regression. But no, it was something different. It had like a mortality name, a morbid. Life,
Like tables?
I have to get back to you. I'll have to dig through my notes.
What is your favorite?
Oh, I would say maybe a paired t-test, because you can compare two groups of data and kind of see what's different right then and there. And I like it because it's pretty simple and it kind of just gets to the point.
Yeah.
Maureen James Cares said, in case Brian wanted to know, sigma equals standard deviation.
That's what it was. Tell her thank you.
Thank you.
Oh, yes.
Yeah.
Thank you. Okay, well, I will turn it.
Question?
Oh, yes.
I just wondered if I know you all do fabulous work, the epicenter you said. Do all of the epicenters around the country, tribal epicenters, do they all provide this kind of training? Or do you know?
I'm not sure, I don't think that all of them have the capacity. I know Northwest Portland does, I know Southern Plains. The others, I'm not sure about.
So I can take that one if you don't mind. It just depends on the epicenter. You know, I know like the Arizona epicenter is really focused on training people like locally how to do surveys, that sort of more community-based stuff. So it really just depends on the epicenter and what the needs of that particular region are.
So if a community, let's say one of your tribal nations did a survey, community or consumption survey, but they didn't have a capacity to analyze the data, is that something that you all can help them with, an epicenter can help them with?
Yep.
So they can send the data to you and work through it together. That's wonderful.
Yeah, we do that on a fairly regular basis. We call them special requests, and we get those for various different projects. So we're happy to help.
I know Albuquerque does more programmatic, more health services.
Right.
Than
They're all different, they're all tribal epicenters, but they all are different. That's one of the things that we've seen a lot is, well, the good news is more and more tribes are wanting to do community surveys on a regular basis. That's great. The challenge is they often say they don't have the capacity to analyze the data. So then they end up getting stuck. Or look for consultants or something if they have the money to, the grant resources to get somebody to help them with that. But
We're here to help.
cool. I love the dog pictures.
So I do have a Courtney. He looks like this one. He's short and fat. He's cute though. And thank you.
Erica, any other questions on your end? All right, let me turn it over to Anna, and I just want to give a brief introduction for Anna. I didn't have my reading glasses earlier, so let me put those on. Anna Garrett is a staff epidemiologist at USET. She is currently developing an emergency management initiative analyzing COVID-19 wastewater data, assisting with the infectious disease competency, among other responsibilities. She obtained her Bachelor of Agriculture and her Master of Public Health with a veterinary public health specialization from the Ohio State University. Anna, I'll turn it over to you.
Alrighty, so now we get to talk about epidemiology, my favorite. So epidemiology links into biostatistics because biostatistics is kind of the basis of epidemiology, how we can kind of prove things. So what we're going to talk about today, we're just going to do a little brief historical context with an example. we're gonna talk about what is epidemiology. We hear that term all the time. So I just wanna go through kind of what it is and then what it can do. We're gonna talk about some core principles and terms, and then we're gonna briefly talk about how to use it. And I do just wanna reiterate, this is just a brief overview of epidemiology. We're definitely not gonna touch on every single thing. So just briefly, some history. The first epidemiologist was actually Hippocrates. He was a Greek physician and also known as the father of medicine. And he kind of wanted to know the logic of sickness, and he wanted to kind of know the relationship between disease, occurrence in the environment. So back in the day, he was wondering if it was maybe caused by the imbalance of the four humors, so air, fire, water, and earth, and if that was maybe causing disease. And he was actually the first one to distinguish between an epidemic, which is visited upon a population, kind of how we know it today, and then an endemic, which is residing in a population. So that was kind of the history of those two terms that we now know today. So now we're going to do a fun example with John Snow. You may have heard of him back in 1854. There was a cholera outbreak in London. And he hypothesized that water was the source of infection. Back in the day, they had no idea why all these people were getting sick. And we'll pull up a little map here if you can see. So all these little dots here are the different cases of cholera. And then we have pump B up here, pump A here, and then pump C. So if you see, all these cases are clustered around in this little London city. And he was wondering why, what is going on here? As you can see, pump A is right here in the middle. So he talked to the residents and was asking them, like, where do you get your water? And most of them said pump A, even the people that lived all in these, farther away areas, even closer to pump B and C. So he found that pump B and C, one was just inconveniently located. They would rather go over to pump A, and then the other one was infected. So they didn't want to drink that water anyway. Now, if you notice here, we have this little 2-block area that there's no cases at all. And he was wondering, why is that? What is going on here? There was actually a brewery right there. So they have their own well, and obviously they were drinking beer. So they had no use for pump A. So they didn't drink any of that water. So that kind of further confirmed his hypothesis that pump A was kind of the source, the waterborne source of the cholera. So then he went to the municipal officials, he told them what he had found, he had talked to the people, his hypothesis, and then they ended up removing the pump. Not surprisingly, the outbreak ended and there were no more cases. So that is kind of the first example of kind of epidemiology classically as we know it. So kind of go through and develop a hypothesis, ask some questions, test your hypothesis, and then you can implement something, some control measure, and then hopefully if you're correct, it works. So what is epidemiology? So it's the study and analysis of the distribution and determinants of health, disease, and events in specified populations. That's kind of the technical term. Basically, it's the method used to find the causes of health outcomes and diseases in populations. And when I'm referring to diseases in this could be any health outcome, disease, event, anything like that. I'm just going to talk about it as a disease just for brevity. It's basically the science behind public health, and it's scientific, systematic, and data-driven. And we determine frequency and patterns. A lot of this is comparison between groups of populations. So if I were to come up here and tell you there's 5 cases of COVID, that wouldn't tell you anything. You don't know out of how many. Is it out of this room? Is it out of Tennessee? Is it out of the US? So a lot of it is kind of comparison based in what specified populations. And it's, like I was saying, also oriented towards groups versus individuals. So we can investigate a ton of different things. We can look at environmental exposures, infectious disease, injuries, non-infectious disease, natural disasters, and terrorism. So basically anything that could be related to any health outcome, disease, event. Different uses, I just listed some of the main ones here, but there are more. You can find the cause of the disease, you can describe the natural history, we can describe the health status of populations, we can evaluate an intervention if it's going well or not, what we can do to improve it. We can investigate epidemics of unknown etiology or origin. We can explain the mechanisms of disease transmission, and we can also search for causes and risk factors, as well as identifying the best types of prevention. So a lot of different things. Some core functions, we can do public health surveillance, we can do field investigation, research, evaluation, and policy development. So very broad scope here. Some just core principles and terms you may be able to kind of take home with you today. Two different kind of key terms is prevalence and incidence. So you may have heard these terms kind of thrown around on the news lately, but prevalence is the occurrence of existing disease within a population, which could be new cases or already occurring cases. And it's basically the proportion of a population with that disease at a specific time or over time period. We have incidence, and that's only the new cases of disease. Just in that population, and incidence is mainly focused on the change. So if, for example, you had a low prevalence and a high incidence, that would be a disease causing rapid either death or recovery. So not many people would be staying in that disease state for long, even though many members of the population are getting it. On the other hand, you could have a high prevalence and a low incidence, meaning these would be kind of chronic incurable diseases where not many people are getting it, but a lot of people are living with it, if that makes sense. So no panic, I just put some 3 basic calculations up here, just kind of to show the broadness of what we can kind of characterize with epidemiology. So the first thing is the attack rate. So this would be the number of the new cases of a disease during a specified time period, and all these are going to be during a specified time period and within a certain population, divided by the number of people in the population at the start of the period. So basically, it's the proportion of the initially disease-free population that gets and develops the disease during that time period. We have the incidence rate, which is kind of similar. So it's still the same new number of cases of disease within a specified period, but we're actually dividing by the time. So the time each person was observed total for all people. So this is kind of more of a ratio of the number of people divided by time. And then finally, we have the prevalence rate, which is the number of new and then also pre-existing cases during that period divided by the number of people in the population during that period. So that's more of a proportion. So the attack rate and the prevalence rate are kind of similar, being that they're kind of divided by the population, just kind of if we're talking about new or new and existing, whereas the incidence rate, the denominator is time. So we can kind of calculate a lot of different things depending on what you may want to look at. Some other terms to know that I think it's important to differentiate. An outbreak, so that would be the occurrence of new case or cases of a disease in a previously unexposed population. So an outbreak is usually more of a local thing. So say you went to a really fun picnic, ate some potato salad, and suddenly everyone has food poisoning. That would be an outbreak. An endemic, so this is the ongoing presence of a disease or agent or health condition in a population, and this is kind of the base level that's usually observed in the population. So it could be 0 if there's never been a case before of XYZ disease, or it could be usually 2% of the population has this disease. Basically, it's just what is normal in the population. An epidemic is similar to an outbreak. It's just on a little bit bigger of a scale. So versus maybe a neighborhood, it could be, a city or a state. So an epidemic is a rapid sudden occurrence of disease in a population above what is normally expected in a geographic area. So it'd be going from that endemic disease state, suddenly have a sharp increase in cases. That would be an epidemic. And then a pandemic, I'm sure that we're all well aware, is an epidemic that has spread over several, countries, continents, the world. So descriptive epidemiology, we're basically characterizing an outbreak in terms of person, place, and time. We'll go into a second what an epidemic curve is, and then we can briefly talk about maps, but basically you can plot the cases on a map and see, like we talked about originally with the cholera outbreak, where they might be occurring, if it's kind of a cluster of cases or if it's spread out, and that can also help you determine. So we're asking kind of 5 questions here. What is going on? What's the diagnosis? What's the event? What are we looking for? Who? What's the population getting the disease or who's at risk? Where's our specific geographic kind of area we're looking at here? When? What time period are we talking about today? Are we trying to characterize something from the past? And then why and how? So are there any risk factors or transmission or anything like that we want to know? So this is the puzzle we're trying to solve. So how do we use this? So an epidemic curve is the visual display of the onset of illness. So we're going to go over some examples in a second, but you're basically going to just plot your cases on a graph based on time. You're going to see a fun curve, and then we'll go over kind of what that might mean. So it helps you determine the distribution of cases over time, if they're all happening the same day, if it's spread out over maybe like a week or a month. If there are any outliers, so any kind of cases that maybe started 2 weeks before all the other ones, a sense of magnitude. So is this, how serious of an issue is this? Is it a lot of people? Is it not that many? Inferences about transmission. So we'll go over in a second how you can kind of determine what type of transmission might be going on. And then a likely time period of exposure. We're not necessarily going to touch on this. It's a little bit of math, but we can figure that out as well. So we have 4 kind of basic example curves. So the point source curve, the one over on your top left, I guess, of your screen for the virtual people, it's the people exposed to a common source. So a common source would be one source. So say, like back in that first example, that pump, be one group of people exposed to one source, but it would be over a brief time period, so one incubation period. So it could be, say, like a foodborne outbreak at a picnic, everyone's exposed all at one time to that potato salad or something like that. And it only goes on for one incubation period. We have a continuous source outbreak, which you can see looks kind of similar where all the cases are grouped together. We have kind of a gradual increase and then it kind of plateaus. So this would be exposed to that common source, that one source, over a period of days, weeks, months, however long. And this would be greater than one incubation period. We have an intermittent source. You can see there's kind of different little kind of tiny point sources all in one graph. These would be people exposed intermittently to that source. There's no relation to any incubation period. So I don't know, say you have the biggest vat of potato salad ever, you could have, they ate it on Monday and then they ate it Wednesday and then they ate some on Sunday, different groups of people. I don't know, that probably wouldn't happen. But that would be a good example of an intermittent source. So it's just one source, but people are being exposed all at different time periods. We have a propagated source. So you can see itty bitty one, we have a little bit bigger curve and then a bigger curve. So this would be indicative of the disease being spread person to person. So you would have waves of infection. So the first wave would be small, maybe just a few people. Those people, they get it, they're in their infectious period, and they're spreading it to other people. Those people get it, infectious period, spreading it to other people. So that would be separated by about one incubation period. So that's how you can tell the difference between a propagated source and an intermittent source, just that kind of incubation period time, if it seems to be kind of the same, or if it could be completely random. So now we have some fun examples. So say we have this nice little graph of cases of cholera. I just made up the disease sources. So this is obviously not real, but what do you think this might be. So we have kind of a gradual increase and then kind of a plateau. Any guesses? That's okay. It's a continuous common source outbreak. Yay. All right, so say we have cases of norovirus. What do we think this is? A point source. So this is just an example. They don't all have to be smushed all the way together. Obviously, these are pictures. If you do graphs like this in real life, they're not gonna look this perfect at all. You're gonna have to have some more interpretation, and you'll probably have to do some calculations. So these are just kind of examples. How about, what if we have these cases of tetanus, kind of different groups of cases all randomly in there, no pattern to the number of days in between. Common intermittent source. And then, as we all know, what if we had cases of COVID-19? Propagated source, yes, correct. All right, so moving on, another kind of key principle of epidemiology, we have the epidemiologic triad. So this is the causal model for infectious disease. We have this nice triangle here. One thing that we're looking at is the agent or the pathogen or whatever, the source might be of that disease. It could be the microbe that causes disease. So we want to consider what characteristics that might have. We also want to consider the characteristics of the host, and that would be the organism harboring the disease. And then the environment, so what kind of characteristics about the external factors of transmission could we consider? So to have infectious disease, you have to have all three of these. So this is kind of sometimes what we think about when we think about, decreasing transmission. If we target 1, 2, or 3 of these, we can really help reduce transmission. So just knowing the characteristics, some things we can change, some things we can't. So host, age, if they're immunocompromised, stuff like that, we can't change, but we could change other characteristics. Say if they wanted to get a vaccine, they'd be more resistant to that agent. For the environment, say we go in with our little Clorox wipe and we wipe off all the COVID, that's going to reduce the transmission. So lots of different things to consider. Another fun thing to consider, vectors. So this would be the person, animal, or microorganism that carries or transmits the infectious pathogen. So this would be for like a vector-borne disease, say like a mosquito or a tick or something like that, something that's helping in this transmission. So just some examples of things that we can do if we understand how disease or infectious disease is caused. We can kind of target how we want to reduce that transmission. Now, just briefly, some steps of an outbreak investigation, which we kind of covered at the beginning. So the first one is to establish the existence of an outbreak. And this may sound simple, but sometimes it might be they change the type of diagnostic test at the laboratory and it's more sensitive. So now we're getting more cases. And it's just, that diagnostic test that changed, it's not necessarily, the prevalence of disease in that population that changed. We want to verify the diagnosis, make sure we know exactly what it is that we're dealing with. We want to define and identify cases. So for our case definition, we want to be very specific on what geographic area we're talking about, what time period, all those certain things, so we can really narrow down what we're talking about. We want to do that descriptive epidemiology. We talked about who, what, when, where, why, and how, determining who might be at risk. We're going to develop our hypothesis, evaluate it, reconsider it, and then we're going to implement control measures. And then very important, we're going to communicate our findings for others so that they can take precautions, they can learn from our lessons. So very important to one, just make sure we do have an outbreak, follow our steps, and then just make sure we're communicating with others. We're going to briefly talk about some study designs because it is important. So we have this nice little flow chart here, so we can have experimental or non-experimental. So non-experimental would be kind of observational kind of studies, probably what we're kind of more used to talking about with public health. The experimental would be either like a randomized control trial or like either a non-randomized trial. We're not necessarily going to talk about that today, but that would be kind of your classic experimental design. For the observational studies, we can either have a population-based or just an individual-based. So individual-based could be like a case report if you notice, you know, an interesting case, you want to write it up, or if you have a series of cases you'd like to write up. We're going to talk about the other ones in just a second, but the population-based ones are more describing what's going on in a population, like a health survey or, you know, ecological survey, something like that. So a cross-sectional study, and these three are kind of similar but different, so I just wanted to quickly differentiate between them. The cross-sectional study is a single sample from a large population containing 2 or more groups in the sample, and this is going to help you determine prevalence. And it's not based on exposure or outcome. You're just kind of taking a group and seeing what you see. We have a case control study. So this is going to compare risk factors between cases or those with the disease, and then controls those without the disease. And then this is going to be based on outcome. There are a lot of, you know, different fancy things you can get into with all these different subcategories, but just kind of basically what they are. We have a cohort study, and that's comparing the outcomes between the exposed and the non-exposed groups to be a risk factor for disease. And this is based on exposure. So that can be kind of confusing, but what really helped me was this little graphic. This is kind of time. So the cross-sectional study, you know, we're just going along and we just pick out a group from the population. We just see what the exposure is and outcome. If we have a case control, just going along in time, we pick out the outcomes we want, and then we look back to see what their exposures might have been. Cohort is the opposite. We pick a group of people based on their exposure, and then we look forward to see what outcomes might be, if that makes sense. So those are kind of the 3 different kind of study designs that are similar, but very different. And you can pick each one of these. Don't panic, we're not going through them. I just wanted to have this here for reference, but we go through units of study, description, what you want advantages, limitations. So if you're thinking about making a study, you just want to kind of think about what you want to find out and then base your study on that. So you can, you know, read through that at your own time, but they all have their different advantages and different limitations. And then you can use epidemiology we kind of talked about before to make some conclusions, and you can use the biostats to prove your point or see what's going on. So that was a brief overview of epidemiology. Contact information here for me and the epicenter, and then I can take questions.
So we really use that every day, especially with COVID. I mean, you know, we're like constantly, we have events. We know 5 to 7 days we're gonna have woohoo, you know, so it is useful. We use it every day, even though we don't know we're using it.
Exactly.
Does that make sense?
Yeah, I'm interested to hear if anybody drawing a connection between biostats and epi in relation to their homework that they do. How do you guys use these tools, even if you didn't realize that you were using them?
I mean, we had, just from my personal experience, a lot of congregate activity in one particular place. So it did, have me be able to raise to our upper council, you know, perhaps looking at what's happening in this place right here, we may need to change practice for a couple of weeks, months, 1 month, whatever. So I think if you have somebody that, you know, in your organization that has their pulse on different testings or different disease processes that are coming to 1 or 2 different places, that person can actually be a great resource guide to kind of head off some worsening conditions or people. So.
Anybody else?
You know, Hannah brought it up a little bit when she started because an environmental health coordinator in our clinic that does what she mentioned, basically weekly assess the wastewater with the wastewater department. So we know COVID cases to a certain extent are going to increase before we see them in the clinic, because that's where they are found first, is you start to see increased numbers in the COVID counts in the wastewater, and it's almost like, all right, here we go, next week it's directly affecting us, because it inevitably does.
Are y'all getting your monthly COVID reports?
What's that?
We produce monthly COVID reports. Are y'all all getting them from your tribal leadership and your board and or your health director?
Yes.
And Monty and Anna and Corella, who's not here, who worked really hard at getting those out. And we recently added the wastewater data in.
Where are you from? I'm from Scott, I'm on Maine.
Who works in a clinic here? Anybody else want to share, either, personally, professionally, thank you, about how epi and biostats affects either their personal life or their professional life? Because we do use it a lot. And we
I didn't understand that.
So scary. Are there any other questions? Erica, who's the online moderator, is texting me the questions because I can't see them. So Erica? Okay, she says no questions. So we do have an evaluation. If you guys wouldn't mind filling it out, we could pass these around. We were going to have an app, but we couldn't get that to work, so we had to get paper evaluations. If you could please fill these out and then put it in the evaluation box at the front desk where you checked in, would really appreciate it. So one of the things that we use all the time that we provide back to the tribal nations is our GIPR numbers. That we pull together for you guys in your diabetes rates and things like that. So it's not just infectious disease, it's chronic diseases as well. And if you notice, your GIPR rates have a confidence interval built into them. What do they call it in GIPR language? It's not confidence interval, it's something else. Yes.
Do you have any more?
Yes.
What did you say about?
On the GIPR report, it has the confidence interval, they don't call it that. They call it something else. Where they have the rate and then they say, well, it could be between this and this rate for real. That's the confidence interval.
Confidence intervals are something that I look at all the time. I'm always looking for an arrow. I want to see an arrow. Sometimes you see it. It's all the way from a negative number to something that's past 100%. Maybe this is really not any.
It's not useful. And unfortunately, with our populations that we serve being smaller, that often happens, unfortunately. Let me check my phone, make sure there's no. I want to make sure there's no questions coming in. Okay. So yeah, y'all can just drop those at the registration desk, and I know that there are sessions coming up. Sorry, Brian. Almost 11, so we've got a break until 11:15, and then we have breakout sessions again from 11:15 to 12:15. If you are, there's no there's no data track for 11:15 to 12:15, but there will be at 2 to 3:15 on GIPR with Christina Rogers.
And y'all may be getting some awards. So you may want to be in the,
For your GIPRA improvement
from 2020.
from 2020, yeah.
2020.
Because we haven't met.
Has it been that long?
Yeah.
2019?
Yeah,
Yeah.
Or,
you know, we get the most improved GIPRA number award.
I tell you, it's been a tough one though, especially with trying to do live patients in the clinic during the beginning of the outbreak. GIPRA was terrible. It was for us anyway, you know, it was, you all have to tell them.
I think everybody was in the same boat.
We're just now getting back into the saddle.
I think that concludes these sessions. Feel free to ask any of us any questions, if you have any during the conference. Amani Ransby is also an epidemiologist, so you could field any questions to her as well. Thank y'all for coming. Thank you.
Thank you.